Okay, here in the final problem, I'm just going to hope that you read over the problem to kind of make this video a little quicker. So read over it, pause this, read over it, and I'm just going to jump into part A. So drawing out this process, we have an evaporator, and we have a inlet stream, and that inlet stream M1 has 0.196 H2SO4, so 19% H2SO4, and then 80% water. We have an evaporator, like I said. We have, from the evaporator, we have a stream going to a crystallizer. And the stream leaving the crystallizer is the filter cake. And so the filter cake has a solution, which is M2, and that is 40%, what is this? Oh, K2SO4. Maybe I should have read out the problem. K2SO4. And 60% water. And so we have the solution, and then we also have 10 times, where's that information in here? Just so I can point that out to you. Oh yeah, and a ratio of the wet filter cake contains solid K2SO4 crystals and a 48% K2SO4 solution, and a ratio of 10 kilograms of crystals per kilogram of solution. So 10 times M2 kilograms K2SO4. That's the filter cake. And then from the crystallizer, we have a stream that is recycled back to the beginning of the process. And this is going to be our M3. And that is 40% K2SO4 and 60% water. So then we have this stream, and it has a certain mass of K2SO4, and it has a certain mass of water. And these are all flow rates. And then leaving from the evaporator, we are told that we have, at maximum capacity, we have 175 kilograms of water per second. And we are working at maximum capacity. So we are also told that 45% of the water fed to the evaporator is evaporated. So that's 45% of what's fed in, the water that's fed in. And then we have this stream leaving the evaporator, and that has a certain flow rate of K2SO4 and a certain flow rate of water. And now we're going to do a degree of freedom analysis on the overall process, as well as the units within it. So degree of freedom overall. So two unknowns, that is M1 and M2, beginning and end of the process. Just drawing a box around that. Two unknowns, and then we can do two balances. That is on the K2SO4 and the water. And then, so that leaves us with the degree of freedom of 0. Now, degrees of freedom on, let's see, mixing point. So on the mixing point, we have 4 unknowns. That's M1, M3, M4, M5, minus 2 balances, K2SO4, water, degree of freedom is 2. Now, degree of freedom on the evaporator, we have 4 unknowns, which are M4, M5, M6, M7. Two balances, K2SO4, and water. And then one piece of extra information, and that is that we know that 45% of the water entering the evaporator is evaporated and leaves the process. So a degree of freedom of 1, and then a degree of freedom analysis on the crystallizer. And we see that we have 4 unknowns, which are M6, M7, M2, M3. And we can do 2 balances again, K2SO4 and water. And we have a degree of freedom of 2. So what we're going to do here, what we're asked to do, is draw a label flowchart. We did the degree of freedom analysis. Now we're going to write in an efficient order, which means minimizing simultaneous equations. The equations that we would solve to determine all unknown stream variables. Again, it says circle the variable which you want to solve, but don't do the calculations. We are going to do some calculations. Sorry. So overall balance. Let's start there. So we have that M1 equals 175 plus 10 M2 plus M2. Now, if we do a K2SO4 overall, we see that we have 0.196 M1 is equal to 10 M2 plus 0.4 M2. Now we can do a balance around this, and not balance, linear equation, solve the linear equations. See that M1 equals 175 plus 11 M2, and 0.196, 175 plus 11 M2 equals 10 M2 plus 0.4 M2. My phone's about to die, so I'm gonna just tell you what M1 and M2 are. I know you can do linear equations. 4.16 kilograms per second, 221 kilograms per second for M2. I just want to get through this full problem before it dies. Now let's see, using the 45% information, we know that 0.45 M5 equals 175. Therefore, we know M5 is equal to 389 kilograms per second. Now, let me move on to the extra page that I included. All right, so we have here that we're going to do an H2O balance on the mixing point. So 0.804 M1 plus 0.6 M3 equals M5. Now we know M5 and we know M1 because we just calculated that on the previous page. Do some algebra, you get that M3 equals 352 kilograms per second. Now let's do an overall balance. On mixing point. So M1 plus M3 equals M4 plus M5. We know all of the variables except for M4, which is we're going to find is equal to 184 kilograms per second. K2SO4 balance around the evaporator. M4 equals M6. So M6 also equals 184 kilograms per second. Let's see, nope, phone's still going. Okay, we got this. So close. Okay. H2O around the evaporator. M5 is equal to 175 plus M7. M7, we're going to find is equal to 214 kilograms per second. And that's just using M5 that we found on the previous page. Now let's do part B. Part B, we're asked to calculate the maximum production rate of solid K2SO4 and the rate at which fresh feed must be supplied to achieve this production. So production rate of crystals is equal to 10 M2, which is equal to 41.6 kilograms per second. And fresh feed is equal to M1, which is equal to 221 kilograms per second. Now part C, we want the composition and feed rate of the stream entering the crystallizer if the process is scaled to 75% of maximum capacity. So at 75% maximum capacity, we have 0.75 M6 plus M7. Let's see, where am I at?